What is the cosmic microwave background? For that, I'm going to have to give a little bit of history about the universe. Most people know right now that the universe is expanding. So if we go backwards in time, the universe will actually be a lot smaller. What happens to everything inside the universe if the universe itself gets a lot smaller? It gets a lot denser. It gets a lot hotter. At that early period, we will actually have a hot soup of elementary particles. There's going to be protons and electrons and photons in there. Now, if we turn the film in the other direction and let the universe expand again, as it expands, it gets colder and colder and colder. There's a certain point when these electrons and protons in the early universe no longer interact with the photons that were there. When I say photons, I just mean light, basically. So after a certain point in the early universe, we've got a bunch of light that was there that no longer does anything with the rest of the matter in the universe. And it just continues to travel throughout the universe until it hits us today. So in a very real sense, the cosmic microwave, and this is the cosmic microwave background, excuse me. And so in a very real sense, the cosmic microwave background is a baby picture of the universe. It's actually light that's coming from the early universe and that has not done anything since that point in the early universe. How was the cosmic microwave background actually discovered? It's a funny story because the cosmic microwave background was actually discovered by accident. There were two researchers at Bell Labs in New Jersey, and they were using a large radio telescope to try and look at the sky in order to measure the backgrounds that we might see when we were communicating with satellites. What happened? They were looking at the sky and they were getting a strange radiation from all over. They had no idea what it was. There's a lot of history behind this. People tell stories about how they were getting rid of pigeons that had been living in the telescope. They had to clean up the pigeon droppings because they thought these things might actually be creating the spurious signal. But even after they cleaned up everything, and they had looked for a long time, they still saw a signal. And the weird thing about this signal was that it was the same no matter where they looked. When they look over in one direction, they saw exactly the same signal that they would see when they looked at another direction. This is really kind of strange for an astronomical thing. You can imagine if you're looking at a star or a galaxy in one direction, you're not going to see the same thing in another direction. When you look up at the sky now, you'll see certain things in one direction, certain galaxies are Milky Way, and you'll see something else when you look in another direction. They saw something that was actually completely uniform. And it turns out, we now know, that this was actually the cosmic microwave background radiation. Penzias and Wilson, the two researchers, actually won the Nobel Prize for this in the late 1970s. Okay, one thing I would note about the cosmic microwave background is, again, it's all around us. In fact, when you're looking at your television and you see snow on the television, about 3% of that snow is actually coming from the cosmic microwave background radiation. So what does the CMB tell us? And how do we explain the difference between what we see in the CMB, which says that the early universe was very smooth. As I said before, when we look in one direction, we see exactly the same thing as what we see in another direction. But when we look at the sky today, we see the Milky Way in one direction, we see external galaxies in another direction. How did we go from the early universe that was very smooth to what we see in the sky today, where we have planets, we have galaxies, we have solar systems, we have clusters of galaxies? How did you go from something where there was no structure to something where there is a lot of structure? One of the tools that we have to do this is the cosmic microwave background radiation. If we look at the cosmic microwave background radiation a little closer, I said before it was very smooth, but it can't be perfectly smooth if we're going to try and explain structures we see in the universe today. there had to be some small, what we call anisotropies, which basically means non-smoothnesses. First thing we do is if we look at fine detail on the cosmic microwave background, we sort of subtract the mean of the cosmic microwave background, we suddenly do see a very small variation. In fact, it looks strange. When we look at a map of the entire sky, it looks like the cosmic microwave background radiation is a little more energetic in one direction than in the other direction. And that's explained because our solar system is actually traveling with respect to the cosmic microwave background. It's traveling in this direction, for example, so that the CMB photons that are coming to us from this direction are actually a little more energetic than photons that are coming from this direction here. And we call that the dipole anisotropy. And that's interesting. It tells us about our velocity in the universe. But it doesn't really tell us anything cosmological. It tells us about what we're doing. It doesn't tell us about what was happening in the very early universe. So we understand our velocity in the universe fairly well, and we can also remove this dipole anisotropy from our maps of the CMB. And the first time this was done was by the COBE experiment in the early 90s, basically. And what they found was a map of the sky that looked something like this. Okay, this is actually made by a later satellite, which I'll talk about in a little bit. But what they found was essentially you have a lot of emission in one plane. This is our galaxy. This is the Milky Way here. But above and below that, you see small variations here and here. I can turn the universe upside down if I want. And these are actually what we call primordial structures. These small variations are the things that actually grew under gravitational weight into the structures that we see today, the superclusters of other material that we see today. So as I mentioned before, COBE was the first satellite experiment to detect what we call these anisotropies, the little variations. There have been a slew of ground-based telescopes, things at the South Pole, in Hawaii, on islands in the Canary Islands, all over the world, basically, to measure the microwave emission of these anisotropies. One of the most recent is an experiment called WMAP, which is a satellite launched by NASA. And an upcoming experiment is called the Planck satellite, and that's being launched by the European Space Agency in collaboration with a number of universities in the United States, Europe, Canada, and all over the world, really. I'm going to talk a little bit about Planck now. WMAP has done a really nice measurement of the anisotropies, but we can do better. Planck is designed to be more sensitive than the WMAP satellite. And two other important things about Planck are that it will have more frequency bands. This will basically allow it to remove the galaxy much better than WMAP has been able to do. And there's also a technical point in that it will be observing at higher frequencies. And so with roughly the same size telescope, they're actually going to be able to see finer detail than WMAP was able to see and is seeing now. We call the first part the fact that we have to remove galactic emission. Even though the galaxy is mostly here, there's little bits of it up higher, you can see this. And to remove that effectively, we actually have to have as much different frequency information as possible. Planck has 10 different frequency bands, whereas WMAP had 4. So this should give us a better handle on these foregrounds and allow us to do a much better job. Behind me, you see Planck. This is our satellite. At the bottom, there are solar panels and our telemetry. So basically, the Earth is going to be below Planck. Just above that, the box is most of our electronics and things like that. This is how we process the data. Above it are the V-grooves. This is the first stage of the Planck cooling system. Planck actually has to be very cold to do the measurements that it does. And the first step in this cooling stage is actually to radiate most of its heat out into space. Above that, you'll see baffles around a large telescope. The The light will come from essentially in your direction, reflect off the telescope, hit a secondary mirror, and then reflect into the instrument itself. The instrument itself is a very small part of the much larger satellite. This is a balloon of the universe made by the WMAP satellite. The difficult thing about this is that, contrary to a regular globe, a globe of the Earth, you have to imagine that you're looking at the universe from the inside of this globe, because the universe is outside. The Planck satellite will be launched in 2009. One of the interesting things about Planck is that it's actually going to be launched in the same vehicle as a second satellite called the Herschel Space Observatory, the Orbit. One of the interesting things about Planck, and Herschel actually, and WMAP as well, is that they're not going to orbit around the Earth. They're going to be orbiting around the Sun itself at a point called the second Lagrange point, the Earth-Sun second Lagrange point. What that means is if the Sun is here and the Earth is here, the Earth travels around the Sun, of course, we all know that. Our satellite, rather than orbiting around the Earth, is actually going to always be outside of the Earth, and it will orbit around the Earth and always point away from the Earth. The nice thing about that is we have solar panels, which can always be looking at the Sun. We also have telemetry, which can always be pointing at the Earth. Polarization in the cosmic microwave background radiation is the next frontier in our studies. WMAP, ground-based instruments, and COBE have made very good measurements of the temperature anisotropies. But the cosmic microwave background is also polarized. That means that there's a preferred direction for the radiation from the CMB. If we can measure that pattern of directions over the entire sky, we can actually learn a little bit more about the birth of the universe. So why do we want to get to the polarization in the cosmic microwave background radiation? The polarization by itself will add to the information we've learned about the early universe. For example, it will help us understand parameters like how fast the universe is expanding, the density of matter and energy in the universe, things like that. But there's one thing in particular that the cosmic microwave background will, that the polarization in the cosmic microwave background will give us. How did we get here? We talk about a very early universe, but what happened before the first second, say, in the early universe? How did we actually get to that point? There's a theory that we call inflation that tries to describe this. You shouldn't confuse inflation, which is a very technical term for the very, very early universe, a small fraction of a second, with the general expansion of the universe, which is happening from after about a second until today. Those are two separate things. This inflationary theory, first come up with by Alan Guth and a number of other people, tries to explain how we got to what we call the initial conditions. Okay, so how does polarization help us understand that? Well, if, and it's a big if, this is what we're trying to prove, inflation happened, there should be gravitational waves. Gravitational waves will actually bend space. It's an interesting concept. But you can imagine now, polarization has definite directions on the sky. So we can make predictions for what the pattern of polarization on the sky will look like if there are no gravitational waves. For example, it might look like this. So you've got a polarized vector here, and a polarized vector here, and a polarized vector here, and a polarized vector here. Now, if you have gravitational waves going by there, they're actually going to bend space. So whereas before you had a pattern like this and like this, that gravitational wave may actually bend these vectors a little bit. And so if we measure the polarization very, very precisely and note these subtle changes in the geometry of the polarization we've measured, we can actually, this is actually a smoking gun for inflation.